So we'll continue with the lecture on modeling of trace experiments. I will just inform the other students about the forum that there is another live stream. So the link is available in the learning environment under transport modeling. So there should be a direct link to the YouTube live stream. Yes, this is working. Welcome back. So this afternoon I want to introduce the concept of modeling of traces. So the solution of the advection dispersion equation step by step, which is important for the calculation of concentrations of trace experiments at a given point. Before I do that, I would just like to discuss the exercise that I haven't given yesterday. And then I will answer some questions that I see in the chat. So if you have questions, please ask. I will address them. So yesterday I prepared a test which is self-explanatory. You get the response or the result after submitting the test as we agreed. The points do not count for the grade, so this is just self-control for you. Now yesterday I asked you, gave you 3 cases. You want to carry out a tracer test to study the interaction between the swamp and groundwater. River flows into the swamp and no river leaves it. So basically the outflow occurs or by evaporation, which is unlikely, or by seepage. You have a borehole downstream of the swamp. So actually you measure in the groundwater. Please describe the test prior to the experiment. Choose one or more tracers and justify your choice. Now, the case is a bit complicated because if we have surface water on the one hand and groundwater on the other hand. Now, the notion that we work in a swamp involves that maybe we have water of a low acidity. So we actually need to deal with the case of lower acidity or pH, high acidity in that case, lower pH. And which traces do we choose? So for surface water, uranine would not be perfect. We know that eosine has a low pH dependency, but it is also light sensitive. So what we can do is to carry out the experiment at night, or to use eosine and to have a parallel set of containers where we control the photolytic decay, or to use naphthionate. In this case, if we need to use naphthionate, we need much more tracer, at least an order of magnitude more, but we would both solve the problem of low pH. Light sensitivity is a bit smaller for naphthionate, but still there. On the other hand, amidorhodamine or any rhodamine is not an option because the transport from the swamp through the sediments into the groundwater would simply not work. So basically we have to make a compromise. So we need to use light sensitive tracers. We have to take into account pH sensitivity. Of course, you could still use uranine if you take samples and then bring back the pH to 8 before you measure. So measure in the lab. So this would be actually the right solution. Now, test that you carry out prior to the analysis. Take a water sample, measure pH. maybe analyze for chemistry or for stable isotopes. Maybe you can do something with the stable isotopes. A reference to the course of Paul Koeniger. An open swamp should have open water evaporation. You could maybe detect the signal of evaporation. So using data of environmental isotopes could be helpful. Second example. You want to identify the pollution source of a drinking water supply. There are 3 possible sources. It is a fractured aquifer, pH is 6.5. Describe your choice and describe your sampling program. So we need 3 tracers. We are in the groundwater, so amidorodamine, sulforodamine excluded. So we just are stuck with uranine, eosine, maybe pyranine, and naphthionate. Pyranine is the most sensitive to pH, so excluded. So we work with uranine, eosine, naphthionate. There might be a little problem with overlap of emission excitation wavelength between eosine uranine, so this brings pyranine back into the game, because we could actually work with the extinction of pyranine for the parallel measure of uranine and pyranine. So both answers would be correct. So the last one, I didn't do the calculation yet, so we have to go back to the equation. I will provide an answer, or just add a numerical test where you can just check the calculation yourself. The right answer is then in the software, so that you can actually check whether you have understood everything. So there are 2 questions in the chat. First one was, is there a difference between amidorodamine B and amidorodamine G? So I have probably been inconsistent once or twice. So we actually have amidorodamine B and sulforodamine G. So there is no difference, because just one of them exists. So this would be the answer. Yes, if there are no further questions, I will just start with a modeling lecture. And if you have further questions, please ask them. If there is a problem with quality of sound or picture or anything else, please just write this in the chat. I see that we have now the 25 students with us. So the lecture is always available live as a live stream. I then edit it and add the link of the video, which is not live anymore, to the learning room, so that you can actually work with it. Would be nice if you confirm that this works, that you have all the material available, and that you can actually access all the material. If you want just to comment on this in the chat, I would be glad to have a feedback. Now, modeling of traces. Basically, we want to be able to predict the concentration of tracers at a certain point or at a certain time for a given geometry and under certain starting and boundary conditions. So this is the questions. So there are several possible tools for this. We need transport models, and transport models can be subdivided into conceptual models, which are often compartment models. Now, conceptual models have been developed for process engineering, basically by chemists, to simulate what happens with substances that you have in containers, in tubes, in pipes. So to be able to calculate the concentration, but also the travel time, transit time, residence time of these substances in a chemical factory, basically. And you can transfer some of these models to nature and conceptualize nature as a sequence of reservoirs, compartments connected by pipes, and use the mathematical methodology and the mathematical instruments developed for process engineering to actually also describe natural compartments. Now, I did my PhD on conceptual models and compartment modeling. This is quite interesting. It's very well established because it's used also in medical studies. Pharmaceutical studies are based on compartment models. When you just take a pill, basically the concentration of the pill is designed in a way that you reach a target concentration in a certain organ which you want to treat without exceeding concentrations in other organs that may be affected. So if you want to treat your liver, you take a pill, and the compartment model is used to calculate exactly the concentration that you need to cure your liver without affecting your brain. So actually these compartment models are used to calculate concentrations in all the organs of the human body based on empirical studies. And once they are established, you can actually calculate how these substances move through your body. Now you can transfer this exactly to natural environments and establish similar models for natural environments. But we will not do this here because these compartment models are not sufficiently precise to model tracer concentrations for trace experiments. Instead, we will discuss physical models, transport models. These models are solutions of the transport equation. Now we have the transport of water, which for groundwater is described by the Darcy equation. But when water is transported, because of the geometry of sediments and pores, there is also an additional transport and mixing of solutes. And this mixing is described by a differential equation, the transport equation, and this equation can be solved analytically and numerically. I want to start with an example of the application of another analytical solution of the transport equations. These transport equations are called advection dispersion equation. They comprise the advection and the dispersion. This picture shows the Rhine River, and Christian Leitpungut and colleagues adding tracer to the Rhine. The story behind this picture is that I think in 1985 there was a major accident at a chemical factory in Basel, Switzerland, a fire, and as a result of this fire, chemicals got into the Rhine River, toxic chemicals. Now these toxic chemicals traveled down the Rhine River and were a potential threat and danger for water supplies downstream. And many cities along the Rhine actually use water, not directly from the Rhine, but infiltrated water that actually infiltrates from the Rhine River, travels through an aquifer for a couple of 100 meters, and are then actually used. The German word is Uferfiltrat, for drinking water supply. Now the concern was that these chemicals actually get through from the river, through the aquifer into the water supply. And at this point, many water suppliers realized that they didn't have good information about when this chemical will arrive, so how long it travels from Basel to, let's say, Karlsruhe, and then how long it takes to the well. So actually, because there was no knowledge about the transport of pollutants in the Rhine River, people had to be very careful and shut down water supply earlier than necessary and keep it closed for more time. And at this point, it was clear that a Rhine alarm model was needed. A model was needed that could actually predict the transport of solutes and that could predict the concentrations for a given input concentration at stations downstream and at different times downstream. So in order to derive such a Rhine alarm model, you need data. Pure physical modeling of these complex processes is not possible. So the decision was taken to actually do tracer experiments in the Rhine, add non-toxic substances, and follow these substances downstream to actually monitor when a pollutant would arrive at several stations downstream. Now, you see here a picture of one of these experiments. Of course, as you know, based on the lecture that I gave yesterday, you can only use amidorhodamine or sulforhodamine. You cannot use uranine, naphthionate, eosin, pyranine, because they are not stable in surface water. So it was clear that significant amounts of amidorhodamine or sulforhodamine have to be used for the trace experiment. The tracer was injected, and then at several stations downstream, samples were taken. So the breakthrough curve of the tracer was monitored. Once this breakthrough curve was measured, an advection dispersion model that I will develop in the next slides was fitted to these experimental data, which was a huge reduction of data, because instead of all these data, you could reduce the model to just 2 parameters, and with these 2 parameters you could predict the breakthrough curve, travel time, concentrations for pollution events of any magnitude for that section. Now, how does this work? What are the basics and what is the underlying theory of solute transport? When you add a tracer to a river or any substance to a river, it will disperse. A river has turbulent flow, so you have many vortexes, and they actually create a dispersion of substances. And this dispersion downstream of the injection point occurs over the depth of the river, first of all, over the width of the river, which is the transversal dispersion, and then along the river. As a result of dispersion, the concentration, the peak concentration, will drop. So you see that the initial peak will get smaller and smaller because it's dispersed over the depth, width, and finally length of the river. After a certain dispersion length, a full mixing over the depth is achieved. This happens quite quickly because you have many turbulence, a lot of turbulence that actually mixes water down and up. And after a further distance, you will also have complete mixing over the entire width of the river. So this requires more flow distance, but after a certain time you also have full mixing over the width of the river. And from that point on, the problem becomes a one-dimensional problem. It's just one-dimensional mixing along the length of the river. And you get this typical breakthrough curve. Now, the total mass below the curve of everything mixed is the same. We assume conservative behavior, so no photolytic decay, no absorption, but the tracer is spread over a larger and larger volume of water. Now we can already say and note that if we look from a distance, if we look from the side of the river, these dispersion curves have a Gauss shape, a bell shape. So they are symmetric and they have a regular shape. I just see there are some questions coming, and I will just check in a second. Now, if we take a sample at a certain point, so if we stand by the river at a certain location, we take samples, or we even have an instrument to measure the concentration live, we will see that the shape is not bell shape like anymore, that it's asymmetric. The explanation for this phenomenon is easy. You can actually observe dispersion taking place. When you do your first measurement, there is less dispersion yet, and when you do measurements at a later time, there's more dispersion. Because of that, your curve is asymmetric. So remember, concentration versus time, or time versus concentration, is asymmetric. Concentration versus space is symmetric and bell-shaped. Now, I will just address the questions quickly. Yes, the PDF for toxicology is empty. I will replace it. I just tried to do it before the lecture, but I noticed that the PDF was corrupt, so I need some more time to retrieve it. You will have it by tonight. Someone has difficulties to access the material. So the group selection is not activated yet. I will activate it after the lecture. Lecture should be over at 3 o'clock, and then from 4 o'clock group selection will be open. And tomorrow we'll discuss the group selection. Yes, the video will be available. I just explained how this works. We have a live channel, and this live channel is used now to produce videos. Once the lecture is over, I edit the video and I make a copy, which is then it's not listed, so it's available through NHI, through our e-learning portal only. So actually the live lecture is available. You can now follow it, and after the lecture I edit it. I remove the beginning where the sound didn't work, for example, and I then make a copy, rename it, and upload it to NHI, and at NHI you have a link to this video. Now, in the transition between the recalculation of the video and the editing, it might not be available for a short time, but usually 1 hour after the lecture and 2 hours after the lecture you have the copy available. Yes, so I think I hope I could answer your questions. Let's continue with transport. So the dispersion is longitudinal and transversal, and the concentration decreases as a result, and an increasingly large volume of water is contaminated. So this is a problem of pollution. It spreads, and the good thing about it is that the peak concentration gets smaller and smaller. The bad thing is you pollute more and more water. Now, why do we have dispersion? The reason can be found at the micro scale in pores. For example, so in a pore, in a single pore, you have a velocity profile. So some molecules are faster, others are slower, depending on their distance from the pore wall. And this induces already a dispersion, a spread of water. But then pores and pore structures are complex, so water can go either way, through small pores, through large pores, and this induces further dispersion and spreading of velocities. And the funny thing is that nature invents complexity and problems at all scales. This is a fascinating phenomenon. So once you have dealt with the dispersion in pores of different sizes, you will notice that you suddenly get from one geological formation to another one. So instead of gravel, you have sand, and this again creates new dispersion. And this addition of new complexities, new dispersion-inducing differences in geological material actually never really stops. This is why dispersion increases with scale. Now, as a result, your tracer cloud will grow. It grows stronger in the longitudinal direction, in flow direction, and less in the transverse direction. So this is why you get these elliptical shapes as a result. If you have initial injection, which is often called Dirac injection, physicist who defined this type of injection as of infinitely short time and having a unit area, you will then observe the transformation of this Dirac impulse or pulse to a bell shape that is getting wider and wider and wider in one dimension, and if you look in 2 dimensions, you see this growing in both directions, transverse and longitudinal. Now here we can already observe the similarity with the normal distribution and the Gauss curve, which is interesting actually. Now we could assume therefore that the particles are distributed like a normal distribution. However, the standard deviation doesn't make much physical sense. It's a statistical concept. So if we want to use the normal distribution, we have to find or to define a parameter, mean parameter for the advection. So this describes how the stuff moves in one direction. It's quite easy. We can just use the flow velocity for this, and it's actually what's done. So the flow velocity, the average flow velocity, describes or replaces the mean or the average value in the normal distribution. Okay. But we also need something that can be used as a proxy for the standard deviation of the Gauss curve or normal distribution. And this is a bit more complex, and this is where we enter in the discussion of dispersion. Now, when you have a normal distribution, you can describe the mean and the standard deviation. So what do we use to describe the spread or dispersion of a tracer cloud? Now, the parameter that is used is the dispersion coefficient. It has the unit square meter per second. And the dispersion coefficient is defined as the product of the flow velocity v and the dispersivity delta. The dispersivity now is a parameter that does not depend on flow velocity. This is interesting. It depends on the medium. And as we will see, it also depends on scale. So we have the dispersion coefficient. You need to actually be precise with definitions here. We have the dispersion coefficient, d, which is defined as a product of the dispersivity small delta times flow velocity. Just have to remember that. We can also remember that the transverse dispersion or transversal dispersion is more or less a tenth or 0.1 times the longitudinal dispersion. So this is quite helpful. It's 0.1 to 0.2 in normal sediments, 0.1 to 0.2, a tenth to a fifth of the longitudinal dispersion. So we have different dispersivities in flow direction and transverse to the flow direction. You can determine the dispersivity with hydrodynamic experiments, basically tracer experiments, and with column experiments. So you can study this in the laboratory, in the column, or in the field. And this is what we do with trace experiments. The result of dispersivity or the impact of dispersivity is shown in these three graphs. So left we have a normal homogeneous aquifer which has a normal ratio between longitudinal and transverse or transversal dispersivity. You have some hydraulic parameters given here, like a flow Q in cubic meters per second, 165 liters per second, or 0.165 cubic meters. You have a time, 0.01 year, and you have a dispersivity given. Here it's alpha. Alpha and delta are used like as synonyms. Sorry for the confusion. In different literature you find different symbols, so alpha, delta is actually the same, and L stands for longitudinal and T for transversal. So here the ratio is 3:1, and you see the result. Now the example in the middle shows a much smaller dispersivity and a higher ratio between longitudinal and transversal dispersion or dispersivity, and you get this needle shape of the tracer cloud. You remember the case study from the Dead Sea? We have carried out, Elisabeth Krüger has carried out this experiment, and the first experiment didn't provide any result. It was really quite confusing, and we really did not understand well why the result, the experiment failed. Only when we started to model the experiment and look at the dispersivity, we could find an explanation for the first failure of the experiment. By the way, the fact that we didn't get a result in the first experiment led us to study the tracer properties, which I presented this morning. Now, actually, if this is the injection point, of course you have boreholes only given at certain locations. You can't change this. So this would be borehole 1, borehole 2. This was the injection point. And we actually thought that the tracer cloud would spread like this, and that we would get a detection in these boreholes without any problem. However, the tracer cloud just spread like this. And we didn't get any signal in either of the boreholes B1 and B2. So the problem was that we had a very low dispersivity, at least a low transverse dispersivity, and because of that we simply missed the tracer cloud. If you understand the dispersion of tracers, you can at least develop an idea of why a tracer experiment fails, or you can calculate the width of the tracer cloud at a certain distance. Now the right hand example is also interesting. Here we have heterogeneous material, which is normal in fact, so the tracer dispersion is not as regular, and the amount of dispersion changes all the time. The result of these processes is shown here for a column experiment. So we have the column and we inject the tracer, tracer comes out here. Usually we do this as a continuous tracer test, and in the beginning we have a sharp increase of tracer concentration from 0 to 1, let's say, and after a certain distance we get then kind of S shape of the tracer concentration. So this is a result of dispersion, and this as well. So this is the case for continuous injection, actually. Now, this also happens in rivers. In rivers, we have zones with higher flow in the center of the river, and we might even have still zones or zones with much less transport, and where the tracer can get stuck or remain for quite a while. You could even sometimes subdivide the system in two compartments. One, this area where the tracer stays for quite a long time, then the central part, and define an exchange between the two. This has also been done. I've noticed that there are some additional questions. What caused the irregular shape on the right hand side? Yes, simply imagine an aquifer, a normal aquifer. You have sand and gravel and maybe a clay lens. When water flows through this sediment, it will also be dispersed in a different manner in gravel, in sand, and in clay. And because the aquifer is not homogeneous, you actually get additional dispersion, irregular dispersion, as evidenced by this graph on the right hand side. So the regular shape was caused by irregularities of the aquifer, heterogeneity of the aquifer, in fact. The fact that irregularities increase with scale can simply be shown here in this central picture with the river. Imagine you have a river, and the river already is composed of different sediments. You have finer sediments here, coarser sediments in the center. When groundwater flows through this river, let's imagine this is a paleo river. The river has been there some time ago and has been buried. Now groundwater flows through these paleo sediments and through the sediments between this old river. Now, as you see, there is at this very small scale dispersion already in different pores. Then you have dispersion by different packages of sediments. And finally, you leave the river and you get dispersion again because river sediments alternate with completely different sediments. And if you scale this further, you can imagine that you get into another geology, and this was not a fluvial sediment anymore. Maybe it is Aeolian sediment or another type, and dispersion increases even furthermore. The same holds true for fractured aquifers, where the complexity of fractures also increases with scale. Now, a special case is a fractured sandstone, where a tracer can actually move in the fracture, but also diffuse into the sandstone left and right. This is now then a double porosity medium, which can get quite tricky to model. Now, this observation that complexity increases all the time is shown in this graph. It looks boring and not special, but it holds a very special and very important message for you. On the x-axis, you see the distance. So this is the distance over which a tracer experiment has been carried out. So this is a 1 meter, 10 meter, 100 meter, 1000 meter tracer experiment. You rarely find tracer experiments of 10 kilometers because people are too impatient and don't have the resources to do this. So we cover 1 to 1000. The y-axis is the dispersivity. Now let's remember, we have dispersion coefficient d equals velocity v times dispersivity, sometimes written as delta, sometimes written as alpha. Here you see the alpha. How do we get this? We made a trace experiment, we have observations, we fit a Gauss curve to the data. From the fitting, we derive in a manner that I'll show you in a minute the mean velocity and a kind of standard deviation, which is the dispersivity. So we actually fit the dispersivity, we get the dispersivity from fitting a curve to data, and the dispersivity is then plotted in this diagram. Now what we observe here is, I would say, unexpected. The dispersivity is not only a property of the sediment. So somehow we would expect that you have a certain dispersivity for sand, certain dispersivity for gravel, and that maybe it will even somehow be constant over space with increasing length of the flow. But this is not true. We observe, which is very interesting, that actually if you put together many experiments, they are quite similar for limestone, chalk, granite, schist, clay, sandstone, dolomite. This is already mind-boggling, I would say. Surprising, astonishing, unexpected. So number one. Second, you see that dispersivity increases with scale. So I told you that nature always invents new trouble, always creates new variability, new opportunities for dispersion to occur. And the result of this is that we see that dispersivity actually increases with scale. And you can fit a curve to this that is defined by alpha, dispersivity, or delta, if you want, equals 0.1 times x. The dispersivity has a scale of meters, and it is actually 0.1 times the distance of the flow problem. So it seems as if dispersivity is a property of space or of nature to create dispersion opportunities. There has been a talk in Freiburg about someone who stated and claimed that dispersivity is actually a kind of natural law or constant, so that there's always more dispersivity with increasing scale, from the nanoscale to the macro scale. Even observing dust clouds in space, you would actually find dispersion there. Now let's stay with geological material and sediments, and we can claim at least that for many sediments we have a dependency of dispersivity on scale, which is defined by 0.1 times x. This is important for you, as I said, because it's helpful. If you have to estimate dispersivity, you can simply estimate it based on this equation, 0.1 times x. If you make a trace experiment with a length of 100 meters, then your dispersivity is 10. Now, going back to the equation, you then just need the average flow velocity, and you can calculate your dispersion coefficient. Okay. Now, if you introduce a logarithmic scale and try to bring this to larger scales beyond 1,000 meters, to 10,000, 100,000 meters, then you might find, looking at the variability or the deviation, that there is a kind of lack of imagination of nature to invent new trouble, but you still find this line 0.1 times x. So remember this as a kind of simple estimator for dispersivity. Another process that can be observed in nature is diffusion. So diffusion is just driven by a concentration gradient. So you observe diffusion with temperature or with chemical concentrations. This is a much simpler process. The differential equation is given here. So actually you have a kind of constant, and then the concentration gradient, and the diffusion, thick diffusion, is actually defined just by the diffusion constant times the gradient. Now, it is interesting to actually juxtapose or compare diffusion and dispersion. And this is done on this scale. Now, if we look at the thermal diffusion, for example, of salts in water, we observe diffusion coefficients from 10 to the minus 8. The unit here is square centimeter per second, so we have to be careful here because it's centimeter per second with absolute values. Now, proteins in water have a diffusion of 10 to the minus 5. Molecular diffusion of salts and gases in water is 10 to the minus 4 square centimeters per second. Heat, as I have mentioned, in water is 10 to the minus 3. Now, the dispersion that we observe as a result of turbulent flow is orders of magnitudes higher. Eddy or turbulent diffusion, for example, in water or even during evaporation is 10,000 times higher, and eddy or turbulent diffusion in horizontal or surface waters is 10 million times higher than thermal or chemical diffusion in water. So if we have turbulence and dispersion, this is the dominant process, and diffusion is not relevant anymore, I would say, because this is like 10 million times stronger than the diffusion of chemicals or of heat in water. Now let's just have a quick look at equations. And this is not to torture you, this is just to show you how this can be simplified. And I want to actually derive and show you how you get to two beautiful equations that are extremely useful, helpful, and important for you. Now, if we look at the transport of substances in water under turbulent conditions, we have these transport equations to start with. Now, they look complicated, but they just look complicated. In fact, it just says the change of concentration over time. Change of concentration over time. This is what we want to predict. We want to predict the change of concentration. Is a result or equals these three components. And if we have a closer look, we see that this is just per axis. So in x direction, y direction, z direction, they are all similar. So we can just focus on one, and it says that the change in the x direction of the change of concentration in x with the dispersion coefficient. So these are the different components of the change of concentration in one direction. And this is the change of concentration induced by the flow. So this here is actually the advection, the transport of the chemical itself, and this is the spread of the chemical. And both the advection and the convection, if you want, they result in a change of concentration in time. So this is the basic equation for transport. Actually, this is just a mathematical expression of this picture. We have a streamline, and we describe the mass transfer in each direction, and at the same time the transfer of the entire bowl or bubble in one direction, which is the advection. We already know the definition of the dispersion coefficient alpha, which is defined d, which is defined as alpha times velocity, and the velocity is calculated with Pythagoras in three dimensions as v square x, v square y, v square z square root. Okay. Now, as often when you have a complex equation, people try to simplify, and this the problem that we have dispersion coefficients in x, y, z direction which interdepend has been solved by assuming that the dispersivity is actually same and orthogonal, so it doesn't influence each other. So if we introduce this simplification, which is not always correct, but which is necessary to simplify the equation a little bit, we get this new expression of the equation. So we can say that the change of concentration over time equals the dispersion in x direction, dispersion in y direction, and dispersion in z direction, in addition to the longitudinal transport in the x direction. And again, we see this here. This is our transport streamline, and this is how it spreads. Now this is still a differential equation. Now we need to somehow try to simplify this a little bit, and basically we can't solve this in 3 dimensions. So if we want to solve this equation in 3 dimensions, we need a numerical model. So we need a numerical model for flow in I would say oceans, lakes, estuaries. So whenever you have a 3-dimensional problem, you actually need to do a 3-dimensional numerical model of that flow and transport. We'll not go further into this. I will now look at the 2-dimensional case, and this is now how we define our reference system. So the flow from an injection well in one direction x and additional spread in y direction transverse to it. So we have an xy plane, and we assume that the concentration change over depth is not relevant. This is what we assume for aquifers. This is a typical groundwater case. Now, if we define the problem in 2 dimensions, we see that we can simplify a little bit. So there's no change of concentration over z. And now we have a new equation, longitudinal dispersion dl, multiplied with the second derivative of concentration in x direction plus transverse dispersion coefficient dt, multiplied with the second derivative of concentration over y, taking into account the advection, gives the change in concentration. So this differential equation can be solved. We assume that the concentration change over z is 0. We need to define some boundary conditions, so we assume basically that there is no tracer before the experiment. C at starting point is 0 over for x and y and times 0. And we define the injection, the Dirac pulse. So we say that we have a certain mass divided by porosity over thickness of the aquifer. So this is our impulse, our start. And we assume that at the end of the day, at the end of the experiment, concentration will go back to 0. If we have these boundary conditions, we can solve this differential equation and we get this beautiful equation. So this equation describes the transport of tracer in 2 dimensions in an aquifer. In x direction, like flow direction, and y direction, like perpendicular to the flow. So with this equation, we can actually predict the tracer at any place in the xy plane after injection. Now let's have a closer look at this equation. We have the mass of tracer, which is our tracer mass, let's say in grams. We have the porosity of the aquifer, N or Ne often. We have the thickness of the aquifer, H. Now this is our variable for the distance from the injection point in flow direction. So it just tells us how many meters we are downstream of the injection point. 4 P are constants. This is our flow velocity. It's given by Darcy. This is the average flow velocity in the aquifer. This is time, so this is time since injection. And this is the known dispersion coefficient in longitudinal and transverse direction. So this is defined, you remember, by d equals alpha or delta times velocity. And alpha is actually 0.1 times x, and x is the distance. like the distance over which I carry out the trace experiment. So then we have an E function. This is again the distance downstream of injection, flow velocity, time. This is again my dispersion coefficient, time. This is the distance from my main flow axis, y, transverse dispersion, time. So everything can be solved. And I have actually added a two-dimensional calculator that I will quickly present if there is no feedback with my screen in a minute. And you can then just insert numbers here and calculate the concentration at a certain distance downstream of your injection and away from your main flow line at a certain time. Now you have three variables here, and this is quite difficult because usually we don't think in 3 dimensions. So often you assume one of them to be constant. For example, I could assume that I just want to know the concentration on the main flow line going through my injection borehole. So not aside in a perpendicular direction, y, no, straight. In that case, y is 0, and this term simply disappears. Yeah? We still have an impact on transverse dispersion because it reduces the concentration in this direction, but y disappears and I have a simpler formula. I could also, and this is what I usually do, say, okay, I want to have the breakthrough curve at a certain distance. So x becomes a constant. So I want to have the concentration over time at a distance of 100 meters downstream. So this becomes a constant here. And if I'm on the main flow line, this is 0. So then I have a function c of t, just concentration as a function of time, mass injected, porosity, thickness of aquifer. This is now a constant 100. Constant flow velocity is given or can be estimated. And now the time is a variable. So I solve this equation for any time from 0 to 86,400 seconds, so for a full day. This is given by flow velocity and by distance x. This as well, it's 1/10 of this value basically. This is a constant, this is known, this is a variable, and so on, and I can actually get a nice plot of my breakthrough curve at 100 meters below my injection point. So I would like to ask you whether you have the feeling that you understand this equation. I will just get your response like 20 seconds later. In the meantime, I will just draw how this will look like. So I have prepared 2 examples here. One is that we have the concentration as a function of time. So we say that x is constant, 100 meters. We calculate dl as alpha times velocity. Let's say the velocity is 10 to the minus 4 meter per second. Then we have a gradient, 0.01. So this is the kf value, sorry. So my real flow velocity is then 10 to the minus 6. Which goes here. Now I have my alpha. Alpha can be estimated as 0.1 times x. So if it's 100 meters, my alpha is 10 x, sorry. So we then plug in this equation and we would get something like this. As I told you, irregular shape, it's not symmetric. And here we can already mention that the peak of the highest concentration, C max, does not the time of the highest concentration, C max, doesn't correspond to the average flow velocity, because this curve is asymmetric. This is clear. Now I can also solve this equation for a certain time. Let's say after 1 day, or 86,400 seconds. I just plug this into the equation, and now I get a kind of screenshot, a picture of the tracer distribution over space. So I've injected here, and then I see how far the tracer has spread, and this curve is symmetric, as I told you. Okay, all good, understood, which is nice. So we will then move on, and actually now it will get even easier, because we will now move on to one dimension. Before we do that, we can also say that we just want to know the time equation. So this is a simplified equation just giving you the scaled time dependency. We can do this by defining a residence time of the system, which is the average travel time, which is simply calculated from the volume per flow. So if we divide the volume by the flow, we get residence time. And if we then re-express this equation as residence time, we get a normalized function which has the residence time as the given here. So this is a nice addition. By the way, all the theory behind this is explained in the chapter on modeling by Piotr Maloszewski, and I have uploaded this chapter so you can read the anti-derivation in the context of this chapter in the learning environment. You can also define the transverse dispersion. This equation is very useful for calculating the distribution of tracer like perpendicular to the main flow. So it tells you how much water is already polluted and how wide the curve will be as a function of dt. If you are unsure about dt, remember dt, in fact the dispersivity alpha or delta is 1/10 or 1/5 of the longitudinal dispersion that we estimate first. Now let's just consider the one-dimensional case. As I told you, the two-dimensional case is typical for groundwater. So this is what we use to describe flow in groundwater bodies of constant thickness. Now the one-dimensional case is typical for rivers. So this is what we use when we do trace experiment in rivers or in pipes. Yeah. Now this is an example. We inject tracer into the river with a big splash, and then from that start, which we call Dirac pulse or impulse, we get dispersion. In that case, of course, the change of concentration over y and z is not important, like the dispersion over depth is reached very quickly and across the channel also, so we neglect it and we just get a simplified differential equation for the transport, which looks like change of concentration over time is a result of the dispersion in x direction and the advection process, v times change of concentration like with space, which is just the shift. Now this differential equation can be solved. We need to define boundary conditions, which is the injection mass per flow, so mass of tracer divided by flow. We need to define that in the beginning, before the experiment, there was no tracer, and at infinite time there's no tracer either. And for that case, we get this beautiful equation for one-dimensional transport. And this equation tells us that the concentration is a function of space and time. It can be calculated by taking the mass of injection, dividing by the flow, for example, the flow of the river. Then we just look at a certain distance downstream x. We divide by square root 4p times dispersion coefficient longitudinal times t to the power of 3. T is the time. We multiply with the e function, and this term then just has the distance downstream of the injection point, the flow velocity, the time, and again the longitudinal dispersion. This curve is very similar, I think, in fact identical to the normal distribution, to the Gauss curve. And the only difference is that the average of the Gauss curve is now replaced by the average flow velocity. And then instead of the standard deviation, we use the dispersion coefficient. And the dispersion coefficient can be calculated, it has a physical meaning, by alpha times v, dispersivity times v, and dispersivity is 0.1 times x. So with this equation we can calculate the dispersion in rivers or in one-dimensional systems. And this is a universal equation. You can apply it to many different cases. I don't know whether I can convey my fascination for this, but you discover that so many things are actually controlled by dispersion. So you can use this to calculate the dispersion of smoke downstream a factory. In fact, this is the three-dimensional problem. You can describe the dispersion of traces in groundwater, of pollutants in rivers, something you inject into your bloodstream. We shouldn't do that, really. But sometimes there are really surprising applications. For example, if you look at the spread of the coronavirus in some countries, it has the shape of the advection dispersion equation. And now we can argue why this is the case. In other countries it's not the case. But in some countries, actually, the whole event of increase and decrease is described exactly, precisely, to a very high degree by the advection dispersion equation. And now we can argue what the coronavirus has to do with spread of tracers. And you will find some arguments for this. But we will not discuss this here. But I want to point out that it's a very universal equation. Very useful. You could even use this to describe flood waves in rivers. So very simple analytical way of flood propagation in rivers. Now, why flood propagation would behave exactly like this? In this case, you don't look at the solute as the thing to be dispersed, but at the impulse or energy that is dispersed. along the river. And we have an analogy, and we see why the one-dimensional advection dispersion equation even works in this case. Now, from the one-dimensional solution, we can actually derive further applications. For example, if you have the spread of a tracer around a well, you inject into a well, then you can just use the one-dimensional case and multiply it with 2p. So you can actually, the spread of a tracer around a well is in fact one-dimensional because it's symmetric, it's the same in all directions. So you use the one-dimensional problem, you don't even need this two-dimensional one, and just multiply with 2p. Now, we're almost through. I just want to highlight some interesting aspects and simplifications here. So you can introduce the residence time. This is a kind of normalization. And the residence time here is defined by volume divided by Q. So you have a volume of a bathtub, you have a flow into the bathtub. The flow out of the bathtub is the same, inflow, outflow is the same, stationary system. Now the volume of the bathtub divided by the flow in, out gives you the residence time of water in the bathtub. So in a similar way, you can calculate the residence time of water in an aquifer. You could also derive the residence time for reduced one-dimensional system by x divided by velocity. In both cases, you get time as a unit, seconds, and you see that the upper one is just divided by the area. So it's just a one-dimensional case actually. Now, when we have this residence time, we can actually simplify our dispersion equation. And this is done by, and I apologize for that, it was not my idea, introducing a dispersion parameter, which is defined by dispersion coefficient divided by Vx. Now we have to remember, we have the dispersion coefficient, which is dispersivity times flow velocity. Dispersion coefficient d equals dispersivity alpha or delta times flow velocity. Now we introduce a dispersion parameter, which is the dispersion coefficient divided by velocity times x. Now, applying the definition of the dispersion coefficient dl, we see that we can simplify to dispersivity divided by x. And now, knowing that in many cases dispersivity is 0.1 times x, you will see that this is actually 0.1. PD is 0.1 in most cases. So this is what we call a normalization. So we normalize our equation. Why? Because we want to make it scale independent of scale. And you will soon see why this can be very interesting actually. Now if we do this and actually rewrite our equation with PD instead of DL, we can actually get a new curve that is independent of scale and velocity. We have divided by velocity and scale. So we can now compare different trace experiments that have been carried out in systems of different velocity or different scale. Now, this can actually be funny and very revealing, very interesting. We can compare a trace experiment in a huge aquifer that is 10 kilometers long with a column experiment of 0.5 meter. Now, our normal case that I have defined in the beginning, saying that usually DL is dispersivity alpha or delta times v, and alpha is usually 0.1 times x, is number 4. So the case that we have defined as the normal case, as the reference case, is this one, number 4, curve number 4. So this is actually the most common dispersivity, in fact, the most common dispersivity that we observe. But some systems have a higher dispersivity and some have a lower one, and this curve shows us what happens then. Now, let's have a look at number 1. In this case, our dispersivity is much smaller, so it's not 0.1, it's 0.005. In this case, we get almost a Gauss curve, so we see that the tracer movement as a function of time is almost symmetric. So the tracer comes in a bunch. It's a little bit dispersed, but it comes in a bunch. Now, this means that most of the flow velocities are very similar, and that they are very similar to the average velocity. So the time function that we get is very similar to the relative to the residence time. So the x-axis, by the way, is the relative time of the experiment, so the time divided by the residence time. Which means that from the trace experiment we can estimate the residence time. So from our trace experiment we get a good estimation of the residence time. Now, this is interesting, but what is much more interesting is the case that our PD value is much higher than 0.1, for example 2, then we get curve 9. Now what does this mean? I saw there is a question, is T0 residence time the same as Tm in the other equations? In fact, yes, it's both a normalization. So in both cases we try to normalize the system by dividing by velocity and space, yes. Now in this case, that the value instead of being 0.1 is 2, we get a very asymmetrical shape, and we observe that most of the tracer comes very early, but still the residence time of the system is this one. So although the residence time of the system would be, let's say, 50 days, so although the average of all the flows, of all the appearances of solutes over time would yield an average of 50 days, we see that a peak of tracer already appears after 1 or 2 days. And this is what we call preferential flow. And this is why it's so interesting, because it is actually quite typical and happens quite often and surprises us in natural systems. So some systems have preferential flow, and this just means that there are flow connections with high flow velocities. They do not represent the average residence time, but they can lead to early peaks, early breakthroughs that surprise us. The residence time is still much higher, but we observe preferential flow, and now we have a theoretical basis for actually understanding and defining preferential flow. Preferential flow is a phenomenon that occurs if the dispersivity is much larger than 0.1 and leads to the appearance of significant amounts of tracers before the mean residence time. Now, this is still very theoretical, but there are many applications, and I like to give an example here from Israel, where some colleagues of mine have studied the flow of traces through chalk. Chalk, Kreide, is a fractured aquifer. So we have actually, I just need to drink something, just a second. We have we have a fractured aquifer, fractures, and this case was so important because there was a plan to build a pesticide factory on top of the chalk, and the chalk is above an important aquifer in the south of Israel, the Judean aquifer, which is important for water supply, drinking water supply. So the argument was made that it could be done, that you could have a pesticide factory and evaporation ponds to actually separate water from like traces or remnants of pesticides in the produce, because the chalk is so impermeable. And actually tests have been made, and the hydraulic conductivity of the chalk was found to be 10 to the minus 12 to 10 to the minus 14. Now we can make a quick calculation what the travel time would be through the chalk in that case. And this was done, and the result was no problem. It will take thousands of years for the water from an evaporation pond to travel through the chalk down to the aquifer. And actually the decision was taken to have these evaporation ponds. Now, I think you are not surprised to learn that after a couple of years, the product was found at the bottom of the chalk. So it had traveled through the chalk, quite surprisingly for some. Now, first of all, remember, nature always surprises you this way. You shouldn't be surprised, actually, because, and now you understand why, there are systems that have PD values of much larger than 0.1, for example of 2, and these systems exhibit preferential flow. So although we calculate and estimate a mean residence time of 7,000 years, it is possible the tracer shows up after 7 years, as shown in this example. This is just a property of the material that is fractured or heterogeneous and that has preferential flow. And here you see the theoretical concept behind this. Now, this is why we do trace experiments, and when we do trace experiments, we can actually identify systems that have preferential flow as well, which is very important for predicting the transport of solutes in these systems, for example, of pesticides. So this is not a big problem for substances that are where the main mass counts, like chloride. Okay, then we have some chloride arriving earlier, but this is not much of the mass. The main mass will still arrive very, very slowly over a long time, and the mean residence time will be quite high. But for some substances that are very toxic, where already traces can be bad, preferential flow is actually a huge problem and must be included in the assessment. Okay, so we are done now with the theory, and I want now to show you how you can actually get from measurements to these curves. So basically, when you do a trace experiment, you first get such a result. You get a breakthrough curve. You have measurements. So you have different concentrations at different times. It's very important that you cover the peak with, I would say, at least 7 measurements. So one measurement here is not enough. So then your sampling was not okay. So you must have enough measurements in this phase. You can, of course, have less samples here, because here the recession is quite predictable, but in the peak area you must have many measurements. Now, The next thing is that you plot your measurements as a mass curve. You sum up the concentrations multiplied with the average flow. The average flow has to be estimated with Darcy equation. And then you try by multiplying the concentration with flow to actually calculate the mass that you have recovered. And it should correspond to the mass that you have injected. So, number one, you plot your concentration curve. Number two, you plot your mass curve. Number three, you try to fit the advection dispersion model to your data, which is the one-dimensional model or this two-dimensional model. For rivers, one-dimensional, maybe also for alluvial aquifers that are not too wide, and for wide aquifers where you really have two-dimensional spreading, two-dimensional model. And this is how it looks like. So you try to actually find the parameters that reproduce your measurements exactly by changing the average velocity, by changing the dispersion coefficient, longitudinal, transversal, and that's it basically. Sometimes you will see that it doesn't fit, and in this case, but only in this case, you can actually discuss whether you add one or two more curves. In some cases you may have 2 or 3 compartments, and the result that you measure is an overlay, a combination of 2 or 3 advection dispersion equations. In such a case here we see that we have the first advection dispersion equation, which is given here, and then we have a second advection dispersion equation here, and even a third one here. In this case, we should always apply the principle of Occam's razor. The simplest solution is the best solution. So I would never try to introduce 7 advection dispersion equations. So just always take the minimum that is absolutely necessary to explain what you observe. Otherwise, the result will get arbitrary. Now, often you have to develop a conceptual model of your trace of the system that you have traced. So you have your injection point. There's a black box, you cannot see what's inside, and you have your detection point where you measure. So you somehow have to assume what's in between. First of all, you assume that it's homogeneous, that it's one system. But sometimes you might have to consider the case that there are actually subsystems, so that you have 1 or 2 or 3 subsystems, and each one then has a dispersion parameter or dispersion coefficient and an average flow velocity. And I have to mention that the advection dispersion equation is only one possible model, although the most versatile and general one. But you also have the exponential model. So if you have complete mixing and recharge over the entire aquifer, you could also have another dispersion type. But let's stay with the advection dispersion model for the time being. So you actually have to subdivide this, and then you get like percentages going into the first, second, and third one. And each one may have different flow velocities and advection dispersion parameters, PD or DL, and finally you get a combined result. Now you can make this more and more and more complicated. My recommendation is never use more than 3. 2 is okay. In some cases 3 might be justified or necessary. More than 4 can actually not be identified anymore based on data. Quite difficult. If you have more than one tracer, several tracers, it might be possible. Now this is a beautiful example of how tracer experiments actually provide information and work. It's a trace experiment that I've carried out myself some years ago, 17, 18 years ago, when I was working for hydroisotope. The question was the following. There was a water supply at the beautiful Bavarian lake. It was an important water supply. They had a spring discharge of about 1 cubic meter per second, so it was a really big one. And there were bacteria in the spring. So actually the question was why? How did these bacteria get into the spring? So we had to identify the source. The funny thing was that the whole environment of the spring had been re-engineered just before for more than €1 million. So actually they spent all the money they had and it didn't solve the problem. The bacteria still showed up. So when they approached us, they just had some spare money left, some couple of 10,000 euros, and we did a trace experiment to actually identify the source. And we had 3 possible sources that we considered, and each one was associated with a borehole, and I decided to inject uranine, eosin and naphthionate as tracers. We had a pre-experiment with pyranine that was quite close to the borehole, which yielded shocking results because the connection between the borehole and the spring was immediate very, very quickly, showing us that if this specific area was vulnerable, we would be in trouble. Now, we started the investigation program and we actually found 3 breakthrough curves. One for uranine, which is the black one for eosin, which is the gray one, and they were both beautiful and very regular. The injection took place end of December. The experiment was carried out during Christmas and New Year, showing how urgent everything was. And we saw that a couple of days after injection we got a result. So this was not too nice because it showed us that actually these areas were not very well protected, but this was probably not the cause of the pollution. And then we were lucky. We had another injection a bit further from the spring. We injected and the tracer arrived later, so the response was not so immediate 2 weeks later. However, the curve was not regular, so there were like very variable concentrations. This was the naphthionate. The reason for the concentration changing so much was not the naphthionate, I guessed, because it's a stable tracer. I thought first that we just touched the curve so that we just got the fringe of the curve, and because of that it was going up and down, but the concentration was high, so this was also not the cause. And then I realized that we had some snow melt thawing and a rainstorm event, and it correlated perfectly with the drop in concentrations. And this was like the smoking gun, because now we saw that in fact there was a beautiful curve of naphthionate which was destroyed by extra water diluting it. So from that moment on we knew that the source of the pollution was actually lying on the line between the ejection point and the spring. So we started to search and we found it. It was a buried creek, so they just wanted to fill it, and they filled it, but the creek in fact was still active and still contributing water from the road. So everything had to be excavated, refilled correctly, well, and afterward the problem was solved. I would also like to come back to my initial example. I started with the first slide on the alarm model of the Rhine River. I told you that the model was developed to actually produce a prediction model for pollution in the Rhine River. Because of that, some sulfurrhodamine was injected into the river, it was measured, and a model was fitted. Now you know that we can use the one-dimensional model, you know the equation, and this one-dimensional advection dispersion model was actually then fitted to the monitoring results of this experiment, and it provided these beautiful breakthrough curves. You see in this example the measurements, points, and the model for different stations along the Rhine River. So actually, by fitting the model, Christian Leipergut was then able to follow a pollutant along the Rhine River and to predict the decrease in concentration, to predict arrival time, peak concentration, and to predict a time at which most of the tracer or pollutant was gone again. Now you just modify your X and you can then predict this for a station further downstream. Now this had to be repeated for several conditions, high flow, low flow, and basically it provided an excellent model of pollutant transport in the Rhine River, which is still be used as an alarm model for the Rhine River today. And the Environmental Agency of Germany is actually exporting this model now to other countries who face such problems today, like Romania, where you had a mining accident, and similar experiments are still done and carried out and models fitted for countries to develop alarm models which help them to deal with environmental disasters by predicting their peak concentration, arrival time, and extinction time, if you want. Now, these are examples, and you see that surprisingly, nature obeys its own laws. So you see that this is a beautiful example of the advection dispersion equation in a river. And the summary is such a model. So for peak concentration of let's say 150 milligram per cubic meter at Laufenburg, you can predict the concentration, for example, at Kemp's or at other locations further downstream. Now, this can be combined for different media. It can be developed for soils, transfer function of solutes through salts for rivers, for groundwater aquifers, and for reservoirs, surface water drinking reservoirs. I think there is an example right here for Sao Paulo. Sao Paulo relies on water supply from reservoirs, and again, it was important to study how such a reservoir would react if polluted. So in order to study this question, tritium was injected, something we wouldn't necessarily do anymore today, but it's an excellent tracer, behaves as a conservative tracer, and if you know what you're doing and you have the permits to handle these substances, it's also not a problem. So it was actually done by Piotr Maloszewski, and the result was beautiful. So you could actually see the reaction at the intake of the water supply after the injection of the tracer. Beautiful advection dispersion equation, model fitted, and mission completed. So you could actually show that the mass recovery curve was 1. So you got everything back. You had a valid model, and with this model you could actually predict exactly what happens if your reservoir is polluted. Now, the summary is advection dispersion equation has solutions for 1D and 2D. For 3D, you need to do numerical modeling. Usually 3D is used for lakes, estuaries, oceans. 2D is used for groundwater, so this is your job. 1D is used for rivers, it's job of hydrologists, sometimes also yours. Fitting the ADV or ADE to data can help you to predict the breakthrough, and it will help you, and this is why I explained all this, to calculate the mass M, because with this equation you can simulate the response of your aquifer to injected masses, and this will be the crucial tool for you to identify the right amount of tracer used for your trace experiment, because you want to be below a certain maximum concentration, which is the visibility, and you want to be above your detection limit. So I always try to be a factor of 10 below visibility at my detection point and a factor of 10 above detection, rather a factor of 100. And this is possible because the spread between tracer not being seen anymore and detection is quite high. So let's remember the detection limit for Euro 9 is 0.002 milligram per cubic meter, or 0.002 microgram per liter. This is what we can detect. I want to be a factor of 100 above that. So it's 0.2 microgram per liter or 0.2 milligram per cubic meter. And you can just see the tracer at 110 to 150 to 100 milligram per cubic meter or microgram per liter. So the visibility is given, let's say 50 microgram per liter. Below that you don't see the tracer anymore. But I can measure very well 0.2 microgram per liter. I'm a factor of more than 10 below the visibility. And I still have a factor of 100 above the detection limit. So the perfect concentration of my target concentration would be 0.2 microgram per liter or 0.2 milligram per cubic meter. Okay, so this is more or less the lecture. There are some questions. Can we carry out sensitivity analysis to check which parameter is more sensitive? Yes. Now, I will try to do an experiment now. So I have to clean up my screen to avoid a disaster. And I will now open the file with the calculator. You have this file on your in NHI, and we will just do a sensitivity analysis online and live if you want in a second. So I'm ready. Yes, and it works beautifully. I have opened, you will see this in a couple of seconds, a small Excel program that is called Tracer 1D. You have the one-dimensional and two-dimensional version on your on NHI on the e-learning platform. Just try to verify what you see, whether you see this already. It looks like you can already see it. Now, we have time here. All this is just an implementation of the one-dimensional solution of the advection dispersion equation. So I have time defined here, and the model is actually here. So this is the implementation of the one-dimensional solution that you have in your lecture slides. You see this is the mass divided by flow, m divided by q, and then you have x square root for p, and so on. The red dots are actually measurements So this would be the result of a tracer measurement that I have done. And the model can now be modified by changing parameters. For example, I can change the injected mass and increase it. And you see how the tracer curve will actually change. You can also now change the dispersion coefficient, and the dispersion coefficient, for example, can be adjusted or changed here to 0.1. And now we can simulate what happens if we have preferential flow. So we change the dispersion coefficient to 2. And not surprisingly, you observe exactly what is predicted by the equation. We get preferential flow, we get an early peak, and if we want, we can even exaggerate this further and get much higher preferential flow. Now, basically what we do is when we have measurements, we try to find the right dispersion coefficient that matches our curve, and usually what we do is that we adjust the dispersion coefficient and the flow velocity, because this is often not known in groundwater systems. But we can of course also use this approach to simulate the result of different masses, and you can do a sensitivity analysis with this model as well. So I hope I could answer your question. And this would be the lecture for today. You have some material. You have the chapter of the book Traces in Hydrology. I have provided the Excel calculator for 1D and 2D, and I will add first of all an exercise for you to calculate the mass of tracer, and second I will add exercises for you to calculate the maximum concentration using the 1D model for tracer transport for the advection dispersion equation. And I've also promised that I will provide the group voting, so I will provide a tool on the platform where you can actually select your group for the group work that starts after the lecture tomorrow. Yes, thank you for your attention. If you have questions, I will have a look at the chat and I will reply your questions. I will reply to your questions. You can use the chat of YouTube, but you could also use the forum of NHI. And yes, I still regret very much that we could not use the Adobe Connect tool, because I would like to have much more interaction with you and see your reactions. But we had to go for a technically viable and stable solution. So I hope you bear with it. And then see you again tomorrow, and we'll start at 10 o'clock regular with a lecture. The outlook for tomorrow is I have explained how we select the tracer, and I have explained how we try to predict the tracer concentration, how we calculate the tracer concentration. These are two key elements. Now, the advection dispersion equation also tells us when the tracer comes, so we can also plan our sampling strategy accordingly. I already mentioned that we should or could use up to 200 bottles per experiment. Now tomorrow I want to actually discuss the detailed planning of the tracer experiment. So all the preparation that is needed, and this will lead then to an example of the permit application. You'll get the template that I use for all my applications, and we will discuss all the different elements of the permit application that is needed for getting the right to carry out a trace experiment. Maybe 2 comments at the end. Cost of a trace experiment. Now, my rule of thumb is that the trace experiment usually costs between 10 and 20,000 euro. Of course, in some cases you offer them for less, but my experience is that these are just signs of desperation and that this is not sustainable. Preparing trace experiment is quite a lot of work. You need to write the permit. This takes you at least a day if you're experienced. It takes 3 months for you to get this permit accepted. Now during that time you don't work. You need to plan the experiment. You will have more or less 200 samples that you measure. Now the analysis of fluorescence is not difficult, but there is still a laboratory cost of usually 10 euro. Some offer it for 5, but this is not sustainable. 15, 20 is higher end. But still, with 200 samples, you will finally have a cost just for analysis of 2,000 euro. To write the permit, 1 time of work in an engineering office is almost 1,000 euro with some extra work before and afterwards. So you're already at 3,000. Then you have devices that you need to have or lend or refinance, and you need to buy the tracer. So you're at 4,000 or 5,000. And the rest of the time is the work that you spend in the field. So you spend at least 2 days for preparing and executing the experiment, and then a couple of days afterwards to retrieve samplers in the laboratory and writing the report. Now, at the end of the day, this means that a trace experiment costs about 10,000 euro or more, 10 to 20,000 euro. So this was 1 comment, and I actually forgot the second one, but I will remember until tomorrow. So see you tomorrow, and have fun with the exercises that I prepare.